Okay, let's rock and or roll in our discussion of lipids and membranes. Lipids are a very diverse group of biomolecules. They are defined as substances from living organisms that dissolve in nonpolar solvents, not water. Unlike most other things that we've talked about, sugars dissolve in water, amino acids dissolve in water. Lipids, what they're going to do is they're going to aggregate together. Now, they can be separated into a total of 6 different classes. Now, of these 6 different classes, some of them we're going to emphasize and discuss a little bit more than others. For instance, I would go ahead and put at the top fatty acids and their derivatives, triacylglycerols, phospholipids, and I guess isoprenoids. Those would be my top 4. Lipoproteins and sphingolipids, despite sphingolipid being one of my most favorite, I'll say, sciencey words, we're not really going to focus too much heavily on them. Okay, so lipids, fatty acids and their derivatives. Now, fatty acids and their derivatives, they are monocarboxylic acids that generally vary in hydrocarbon chains. So they have a carboxylic acid right here, and then an aliphatic chain. Now, we do follow a numbering or a identification scheme of alpha, beta, gamma, delta, epsilon. That's where I stop. And then the last one is omega. So we do follow that, but the ones that are maybe the most important to you are going to be the alpha and the omega carbons. Now, these are the most important components of several different types of lipid molecules. So this fatty acid is a part of other lipids, which may sound kind of strange, but it's a lipid, but it's also a part of other lipids. We'll get into that in a little while. So most naturally occurring fatty acids have an even number of carbons, so 2, 4, 6, 8, 10, but most of those range between 12 carbons and 20 carbons. We've got 2 classifications for these. They are saturated fatty acids where they have nothing but single bonds, and then we've got unsaturated fatty acids where there is at least one double bond. Now, the implications of that double bond can result in a fatty acid being classified as a cis fatty acid or a trans fatty acid. So based on the groups adjacent to that double bond, it's going to be either a cis fatty acid or a trans fatty acid. Now, unsaturated fatty acids, one or more double bonds, if they are in the cis configuration, which is maybe the most common, you're going to have a kink within that chain. So what we've got here at the top, this would be a cis isomer, whereas B at the bottom here, we've got our R groups, and they are in the trans configuration. Those fatty acids fall into categories of monounsaturated or polyunsaturated. Monounsaturated fatty acid has one double bond. A polyunsaturated fatty acid has more than one double bond. Now, here is essentially what a cis fatty acid is going to look like. So here's a saturated and a polyunsaturated, 1, 2, 3 fatty acid. And what I was talking about was that kink in that double bond. This would be a cis fatty acid because here's our double bond, here's an R group, and then on the same side, here's another R group, R group, R group. So this is a cis fatty acid. But what I'd like you to look at is if you put these right next to one another, they are going to occupy different spaces. And what I mean by that is if you have a bunch of saturated fatty acids, they can pack in really well together. They're right next to each other. Whereas your unsaturated and polyunsaturated fatty acids, now you've got something that, well, let me erase all these guys. You've got a fatty acid that looks like this. You can't have that packaging of tons and tons of them because they're just they're going to repel one another. Now you might be wondering, well, what are the implications of these double bonds? What's the implication of a monounsaturated fatty acid versus saturated fatty acid or a polyunsaturated fatty acid? And I'd like to introduce you to a little bit of, I guess, kind of nomenclature. Here, the convention for labeling a fatty acid is to write a number, which I will use the pound sign, followed by a colon, and then followed by another number. Okay, so this first number, 18 in this case, indicates how many carbons are in that fatty acid. in that fatty acid. This next number, the 0 here after the colon, to the right of the colon, that's going to indicate the number of double bonds. As you can see right here, this is 18 carbons long. There are 0 fatty acids. Okay, and that's stearic acid. That has a melting point of about 70 degrees. Now let's go ahead and make a monounsaturated fatty acid, kind of derivative of stearic acid. Well, that has a different name, and that should be a colon there. That is oleic acid. Now, oleic acid is 18 carbons, has 1 double bond right here. This is a cis fatty acid, R group. The melting point of this fatty acid drops down to 16 degrees Celsius. So 16 degrees Celsius would be something like, I think in the 50s or so Fahrenheit. Now let's make it a polyunsaturated fatty acid with 2 and 3 double bonds. Linoleic acid has 2 double bonds. Linolenic acid has 3 double bonds. And we've gone from 16 degrees Celsius with 1 double bond to -5 degrees Celsius as the melting point and -11 degrees Celsius. So essentially what we're looking at is the more double bonds that are introduced, well then the lower that the melting point is. So what that means is that there's less energy needed to break any sort of intermolecular interactions, and therefore unsaturated fatty acids are more than likely going to be a liquid at room temperature. Now, the naming scheme or the numbering scheme that is used, I just mentioned that we've got this 18 colon system, but this is what's known as the delta configuration or the delta nomenclature. What we have is the number of carbons followed by the number of double bonds, and then we've got a delta. Now that delta is going to tell you where that double bond actually is. So the way that numbering is going to start is from your very first carbon, the carbon within your carboxylic acid. 1, 2, 3, 4, 5, 6, 7, 8, 9. This is a delta 9 or 18:1 delta 9. There's a single double bond and it is found at carbon number 9. So that's essentially what we're looking at with the delta system. If there was a second double bond, say if there was a second double bond between 11 and 12, you would see delta 9, 11. You wouldn't have to indicate another delta or anything like that. Okay, the omega system is similar but different. It's different because your numbering starts from the opposite end of the fatty acid. Okay, now what's unique about this structure right here and the one that we looked at on the previous page, those two fatty acids look the exact same. The reason for that is because of the fact that, well, they are the exact same. Your numbering scheme happens to be basically the same because they're both 18:1. The last one was delta 9. This is omega 9. Now what this is going to do is we're going to start our numbering from our omega carbon. So we're labeling 1, 2, 3, 4, 5, 6, 7, 8, 9. Double bond right there between 9 and 10. So essentially that's what that is going to look like. There we go. Now, fatty acids can also be classified as essential and non-essential fatty acids. Plants and bacteria can make all the fatty acids they require from acetyl-CoA. Mammals obtain most of their fatty acid from their diet. So although they can produce saturated fatty acids and some monounsaturated fatty acids, they can also modify some dietary fatty acids by adding 2 carbon units made from acetyl groups. In some cases can introduce double bonds in the tails. Most of the time they're getting their fatty acids from their diet. So fatty acids can be synthesized, or that can be synthesized, are your non-essential fatty acids. Enzymes required to make fatty acids such as linoleic acid and that would be that's linoleic acid and alpha-linolenic acid. These enzymes are absent. And so therefore, these two fatty acids, linoleic acid and I'll change the alpha to be out here, alpha-linolenic acid are essential fatty acids. So these two were the ones that we looked at just a little while ago. These are polyunsaturated fatty acids. So essential fatty acid examples are linoleic acid and alpha-linolenic acid. Linoleic acid is a polyunsaturated, or it's got 2 double bonds. The delta 9 system, we say delta 9, delta 12, or delta 9, comma 12. The omega numbering system is a little bit different. And the reason for that is we look at where the fatty acid is, or where the first double bond, where the first double bond is, and then we know that the fatty acid, we know that the double bonds are not going to be right next to each other, but instead you have a sequence that is double bond, single, single, double bond. So essentially what that means is if you had a chain that looked like this, double bond, single, single, double bond. So this would be carbon number, let's say it's 6, 7, 8, 9. So we'd be able to say if we have an omega -6, that means that we know that we've got a double bond that's at carbon number 6, and then another double bond that's at carbon number 9. That's the patterning that we can kind of accept based on, or accept with the omega numbering scheme. So same thing down here, and this is actually a typo. This should be a 3 here. Sorry about that. 18:3 omega-3. That means the first double bond is at carbon number 3 to 4. Single, single, double bond, single, single, double bond. So that's what that effectively looks like. You could make the case that the delta numbering scheme is a much more detailed and much more explicit because it tells you exactly where all the double bonds are. But there we go. So linoleic acid is also known as an an omega-6 fatty acid. There's tons of it in vegetable oils, eggs, and in chicken. Alpha-linolenic acid are also known as your omega-3 fatty acids. EPA and DHA are good examples. Sources of these are flaxseed and soybean oil, walnuts, fish, and oils, Mediterranean diet, right? I think that there's lots of, because you eat a lot of fish with that diet. EPA and DHA are thought to have numerous positive cardiovascular health benefits. They're believed to fend off inflammation. Okay, chemical properties of fatty acids, one of which is that they can react with alcohols to form esters. So here is our fatty acid where we have our carboxylic acid, and then here's an example of an alcohol where this hydroxide group is bounced, that hydrogen's gone, and now all of a sudden we've got this fatty acid ester. So unsaturated fatty acids can undergo hydrogenation reactions to form saturated fatty acids. If you think about Crisco, I think Crisco is a hydrogenated fatty acid, which is why it's solid at room temperature and remains solid at room temperature. So you've got the hydrogenation of these polyunsaturated fatty acids. Unsaturated fatty acids are susceptible to oxidation, so that is one kind of risk associated with them. So next up is our triacylglycerols. Now this is kind of a perfect segue from a fatty acid reacting with an alcohol to form a fatty acid ester, because triacylglycerols are just that, a molecule of glycerol and 3 fatty acid molecules. These overall have no charge and therefore are neutral, or they are neutral fats. This is the closest thing that you're going to see when it comes to lipids forming polymers, but these aren't really polymers because it's not a entity that continues to make copies and copies of itself. Fats versus oils. Fats are solid at room temperature, a large proportion of saturated fatty acids. Oils are liquid at room temperature. They are highly unsaturated, and they have a high unsaturated fatty acid content. Triacylglycerols have a number of roles. One, storage. They store energy more efficiently than glycogen. You could think about that in terms of like the packaging, because if you think about a glycerol or a glycogen molecule, it goes on and on and on and has all these branches and takes up a lot of space. And sure, you can get a lot of ATP from each one of these glucose molecules, but compare that to the number of carbons in a fatty acid molecule. Well, those triacylglycerols are going to be packed really well together. They're going to pack all those fatty acids together. So whenever they undergo beta oxidation, you get a lot of energy from those. They're hydrophobic and make very compact structures, and thus contain the same amount of energy as glycogen in about 1/8 of the volume. Triacylglycerols have higher capacity. They can accept more electrons when oxidized, so they can release more energy when they're broken down. And if you think back to the electron transport chain, our entire objective was transporting electrons to make NADH so that we could break that down and transfer electrons through the electron transport chain. Triacylglycerols can also provide insulation, and they can make fur or feathers water repellent. So if you think about like birds' wings or something like that, how the water sort of beads off. Okay, you've got fats there. So triacylglycerol structure, this is it. We've got our glycerol backbone, and then fatty acid, Fa1. We've got our second fatty acid, Fa2, and then our third fatty acid, which is Fa3. And there's our ester linkage between the two of them. Okay, next up, phospholipids. Phospholipids play a number of roles in living systems. They provide structural assistance of membranes. They're amphipathic molecules. When they're suspended in water, they spontaneously form ordered structures. Monolayers, bilayers, and micelles. Property basis of membrane structure. And there are two major types of phospholipids, phosphoglycerides and sphingomyelins. So phosphoglycerides are molecules that contain a glycerol molecule, a fatty acid, a phosphate group, and an alcohol. Okay, so we've got it displayed down here at the bottom. Here's our glycerol, here's our fatty acid, here's another fatty acid, here's our phosphate group, and then, well, we've got another group that can go down here. Either it's an alcohol or there can be a modification to it. Now, these are the most numerous phospholipid molecule in cell membranes. They're classified according to which alcohol becomes esterified to the phosphate group. So this group right here, the one that I've underlined that my head is blocking, is where our modification is going to take place. And here are all of the different molecules that can basically be added in place of that alcohol. So you'll have a phosphoglyceride will have two fatty acids, and then it will have a phosphate, and then one of any number of these things added to it. Water, choline, ethanolamine, serine, glycerol, phosphatidylglycerol, or inositol. All of these are modifications that can be added to that molecule. Now, as you can see, they're quite a bit different from one another. They can be huge or they can be kind of small. In the case of, well, choline or water, it's a small group, whereas phosphatidylglycerol or inositol is absolutely massive. Now, those are all used as kind of signaling molecules and communication between cells, so they all do serve different purposes. Our next group to elaborate on sphingolipids a little bit, these are important components of animal and plant membranes. They contain a long chain amino alcohol. Here is our long chain amino alcohol. Here would be the long chain portion of it. We've got that repeated CH2 12 times. So in animals, this is the most common amino alcohol that you'll see in a sphingolipid. Now, you could kind of think of this as analogous to the glycerol backbone of a triacylglycerol or a glyceride or something like that. But it's obviously got some differences. It doesn't have 3 ester bonds coming off of it. Instead, we've got a fatty acid, and then we've got a head group, much like what we saw with our glycerides. Here would be a phosphate group, and then a modification to that phosphate group. So there are some elements to this that are similar to glyceride, but there are definitely some that are different. I would say first and foremost, the glycerol backbone has some changes to it or has some differences to it. But this sphingomyelin is maybe one of the more common sphingolipids within within animals. Now, with that said, these molecules down here, sphingosine, phytosphingosine, and a ceramide, all kind of serve as the foundations for sphingolipids. So depending on modifications to each of these different groups, you're going to come up with a different sphingolipid. Now, this next group, isoprenoids, are pretty cool because they're kind of simple, but they're actually kind of complicated. So isoprenoids contain repeating 5-carbon isoprene structural units. This would be an example of one of those 5-carbon structural units. These are not synthesized from isoprene. They start from acetyl-CoA. There are two major types of isoprenoids. There are terpenes and steroids. Terpenes make essential plant oils as well as pigment molecules for plants. Steroids are derivatives of cholesterol. So here would be examples of some terpenes. This would be a monoterpene, a sesquiterpene, which has 2 and 3 of those 5-carbon units repeated, a diterpene, triterpene, tetraterpene, and polyterpene. So when you have 8 of these 5-carbon units repeated, you can form a molecule like beta-carotene. So 8 times 5 equals 40 carbons. Now, this is, as you can see, the structures are all very similar to one another, but at some point they reach a junction when they're pretty drastically different. Now, steroids, also isoprenoids. These are complex derivatives of triterpenes. They're composed of 4 fused rings, 2, 3 rings that are 6 carbons, and then a 4th ring, which is only 5 carbons. These are found in all eukaryotes and a small number of bacteria. Now, what makes them different from one another is by the placement of carbon-carbon double bonds and other substituents. The steroid system is nearly flat and very rigid. Cholesterol is an essential component of an animal cell membrane. Now, precursor to this in biosynthesis of steroid hormones, vitamin D, and bile salts, or it is an example of that. This is usually stored within cells as a fatty acid ester. So cholesterol right here has a total of 8 stereocenters. 1, 2, 3, 4, 5, 6, 7, 8. 256 stereoisomers are possible. Now this right here, of those 256, this one displayed right here is a stereoisomer found in human metabolism. Here are a number of different animal steroids that are fairly commonly known: progesterone, testosterone, 17-beta-estradiol, aldosterone, cortisol, cholic acid. They all have that same general structure. Now we're going to go back a bit to talk about lipoproteins. Lipoproteins are any protein that is covalently linked to a lipid. These are classified according to their density. Chylomicrons are a large lipoprotein of extremely low density, and approximately 2% of them is protein. Now, these transport dietary triacylglycerols and cholesterol esters from intestines to muscle and adipose tissue. VLDL, or very low density lipoproteins, they're very low density, approximately 10% protein. These transport lipids to tissue. Okay, so VLDL, they transport those lipids to the tissue so they can be broken down maybe. LDLs are low density lipoproteins, and approximately 24% of them are made up of protein. These carry cholesterol to the tissues. HDL are your highest density lipoproteins, approximately 55% of them is made up of protein. It scavenges excess cholesterol from cell membranes and transports it to the liver for degradation. So when it comes to a membrane, this is a little bit of a jump almost, but we've talked about all the components of membranes without really talking about the composition of a membrane. So a membrane is largely made up of fatty acids and lipids, but they vary quite a bit based on, well, what is the cell type and what is the tissue that's in question. So here are a couple of examples. Carbohydrates, by and large, are a low percentage of a membrane. They are still generally a part of a membrane. Compare that to proteins and lipids. Now, these proteins, one thing that's important to recognize is that proteins can be associated with membranes by being linked to a lipid. Proteins can also be embedded or be like traverse a membrane. So they all do different and unique roles, and they have kind of a pretty dramatic range of what is a protein component and what's a lipid component. Proteins in something like spinach chloroplast, 70% of that is proteins, whereas only 30% is lipids. And this obviously has some error bars to consider because 106%, 70 plus 30 plus 6. So anyway, so membranes undergo some kind of complex and tricky rearrangements. This spontaneous rearrangement that phospholipids undergo is the basis for membrane structure. So membrane lipids are largely responsible for 4 other features of biological membranes. 1, they have to provide enough membrane fluidity, dependent on the number of unsaturated fatty acids. They also basically serve as a barrier. They have to enable and support free transport of charged molecules. They have self-sealing capability in that they are going to control openings and closings for movement to move through, and they are going to be asymmetrical. So lipid composition is different in each bilayer. So this right here to me is maybe one of the most important, one of the 2 most important slides as it comes to membranes and membrane proteins. And that establishes basically the association of proteins with membranes. We've got 2 different displays here. We've got this green guy right here and then this green guy right here. These are both proteins and they both are characterized as peripheral proteins. So what that means is they are associated with the membrane, but they are not embedded into that membrane. Membranes or proteins that are embedded into a membrane, whether they traverse the entire membrane or they've simply entered a portion of it or one side of the bilayer, they're going to be considered integral membrane proteins. So it's important to have those distinctions from one another. Now, the function of each of those can vary quite tremendously. Here, what we see are some examples of integral membrane proteins. We've got, in the context of transport of things across a membrane. One of the things that I'd like you to recognize about this is, well, the simplest way for a metabolite to move across a membrane is for it to simply diffuse. So there's nothing that's actively going to move it across the membrane. It can simply associate with a membrane, migrate through the membrane, dissociate with the membrane. There are other ways in which metabolites can be moved from one side of the membrane to the next, and that would be an example of that would be facilitated diffusion. So this right here, this gold protein would be considered a integral membrane protein that moves molecule X from one side to the other side of the membrane, and it moves it alone. Okay. Now, the next entity or the next option would be kind of 2 different examples. These are known as secondary active transport proteins. So what I'd like you to do is look at, we've got molecule X and we've got molecule Y. Now these are 2 molecules that are moving in opposite directions of one another. So a way that you could think about this taking place is molecule X might favorably move across a membrane. Molecule Y might not favorably move across a membrane. However, X moves so favorably across the membrane, it's able to move molecule Y to the opposite side of the membrane. So this would be an example of a or an antiporter, I'm sorry, because they're moving two molecules in opposite directions. Okay, now if we look at this purple protein, this is moving two molecules across a membrane in the same direction. This would be considered a symporter because it's moving two metabolites across the membrane in the same direction. The last protein that I'd like to mention is this primary active transport. So this is movement of one metabolite from one side of the membrane to the next side of the membrane. And it is driven by the hydrolysis of ATP, making ADP an inorganic phosphate. So it's that hydrolysis that helps move molecule X from one side of the membrane to the next. Now, good example of this would be, or good examples of these are enzymes associated with glucose and with sodium. So I'd first like to show you the sodium-potassium ATPase. Now what this is going to do is it's going to move two molecules, or two ions, sodium and potassium, to opposite sides of the membrane. So the sodium ion moves from the inside of the cell, or inside of the cell to the outside. Potassium is going to be pumped from the outside in. The movement of these two things in combination are favorable for one another. Now, this enzyme over here, glucose permease, well, what it's going to do is it's going to pair the movement of sodium and glucose from the outside to the inside, or the interior side of this membrane. Now, this would be a symporter, and this would be an antiporter. Now, this was a whole bunch of information to take in. I did clip out some slides from the PowerPoint that I posted on Canvas, but I hope this was helpful, and go get them.